Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome to new discussion which is pre-processing of spatial data sets, and here this discussion is in two parts. First we will discuss the basic types and then we will go for some advanced pre-processing of spatial data. So basically these analytical operations in GIS, and there are various ways these can be divided. Some people would like to divide in as primary and secondary operations. Some people will divide in some different way. So in the literature you may find little bit variations, but basically it is in two parts, that the basic operations which we try to do under this primary operation category, and that includes basically the basic functions, usually refers that GIS tools we will be using just to simply measure area, distance along a line for distance, area for a polygon or perimeter, maybe buffer generation along a line or a point or even a polygon. Buffer part we have not discussed yet, but in future we would be definitely covering that part. So buffer generation is also one of the analytical operations, and then reclassification etc. Reclassification, because generally suppose if we are having a continuous data and now we want to reclassify it into different categories. For example, I am having a digital elevation model in which the elevation values are say varying between 100 to 1000 meters. So now I want to classify that map. Instead of displaying or using as a continuous, I can classify say 100 to 200, 201 to 300 and so on and so forth. So depending on my requirements I can reclassify. So this part we will be also discussing how to classify and reclassify. Now when we go for in detail about the area or distance measurements, then there can be two methods. One is the manual method by which we can do it, or auto population in attribute table, because these tools are also available. So suppose if I am having a polyline theme as one of my theme in the GIS database, and now I want to have a field which will have the length of each segment. So that can be done automatically, and it will be this information would be residing in the non-spatial database. Same I can do it for polygon, like I can go for calculation of 3 parameters associated with polygon, maybe area, perimeter and centroid, and all these things can also be done in a completely automatic manner. Only thing which one has to remember, that when you go for such a auto population, please check for random, do the random checks on certain polygons and see whether the area is coming all right or not, because every time you cannot completely depend on the software. Software may be accurate, but if our coordinate system is wrong or our something wrong with our units, then results will also be inaccurate. So in order to avoid that thing, it is always better to check and recheck about the data. Now there are different measurement types. We can have one kind of measurement which are planar measurement, and then another measurement is geodesic measurement. Now planar measurement means basically doing the measurements in 2D. For example, like we use the survey topo sheets or survey or any other map which are in 2D or 2D Cartesian system, and therefore calculating area, perimeter or distances becomes much easier and accurate as well. But when we go for the 3D, then for like geodesic measurements or in 3D measurements, then things becomes little complicated. And especially in the hilly terrain, if somebody is using a digital elevation model or even a satellite image of a hilly terrain, then one has to take care about while doing the area measurement, planimeter, whether that is a planimeter measurement or a terrain measurement. Sometimes we also call as terrain measurement. For example, one use of a geodesic line is when you want to determine the shortest distance between two cities for an aeroplane flight or etc. So, depending on our requirements, we can choose the measurement type, and of course, depending on the what type of data input is there. Whether data has come from a 3D surface, that means a part of the sphere, curved surface, or data has come from a 2D map like survey topo sheets or some other maps. So, depending on that we should do, and the same advice here that after each and every operation in GIS, please check for errors. Now, there are some other measurement types which can also be explored, and for measurements like loxodrome measurement, which is the loxodrome is not a shortest distance between 2 points, but instead defines the line of constant bearing or azimuth. So, instead of going through a curve, if it is a straight line, many of such distances are used mainly for aircrafts or other things, or even maybe for missiles as well. So, depending on if a distance is too large, that means the curvature of the earth will play very important role, and in what projection system you are having your input maps, that will also depend. So, like in this great elliptic, that a line on a spheroid or ellipsoid defined by intersection at the surface by a plane that passes through the center of the spheroid and start and end points of the segment. That means you cannot just handle like a 2D map. You have to take care about these things if the distances are very large. If distances are small, then the curvature of the earth will not play very important role. So, if you are going for measurements even in 2D, assuming that everything in 2D may work very well, but if distances are large, then all such cares are very much required, because error propagates in GIS, and therefore we must take care about all these things in the beginning. Now, there are other measurement types, like for example calculating the aspect of a sloping surface, and that is basically the direction of that sloping surface with reference to the north. So, this aspect for which you require input as a digital elevation model or DEM, and as you know that aspects basically identifies the downslope direction of the maximum rate of the change in value from each cells to its neighbors. So, if it is a sloping surface, then what is the orientation of the sloping surface or direction with reference to north, and that is what is aspect is. Here you are seeing examples also, that this is input digital elevation model, and this is the aspect which has been calculated for this. And aspects generally by default you can calculate in 8 direction, starting from north, northeast, and then east, and likewise, and this is what you are seeing here also. And one category will always come which is for the flat. If your terrain is flat, then obviously it will not have slope, and obviously it will not have aspect, that means the orientation of the slope. So, that category will always be there if that kind of features are present within your digital elevation model. Now, aspect is very useful parameter which comes through a digital elevation models, in many kinds of modeling or analysis, like somebody is working for soil erosion studies. So, they would like to see the aspects of different sloping surface, because maybe the rainfall may not be occurring uniformly in that terrain. Maybe in particularly, generally what happens like in Himalayan conditions, rainfall occurs mainly on the southern facing slopes. Similarly, maybe the snowfall, like for example, if I take example of a Mussoorie ridge, then generally the more rainfall occurs on the south facing slope, which is towards the Dehradun, rather than north facing slope, which is towards the Uttarkasi. Now, so if there is more rainfall, and these are also called the sun facing slopes, the south facing slopes, that means there are more chances of soil erosion. And if that is also, that may be also true in case of landslides also, because the most of the human activities in hilly regions, especially in the cold areas, are concentrated on the southern facing slope, because it receives the sun from morning to evening. And therefore, these slopes are more vulnerable. If you observe the satellite images, you may find that the north facing slopes are generally full of vegetation or forest, but south facing slopes are devoid of forest or very little vegetation you may find, because of human activities, because of the sun, because of the the soil erosion, and because of the landslides. So, these things the aspect of slope or direction of sloping surface with reference to the north is very, very important, and it is very useful also. People also use in like those who are working in hydrology or prediction of discharge in a stream which is snow fed or glacier fed, then again the aspect of a slope is very important, because that receives the sun, more melting will occur on the south facing slopes. So, therefore, this parameter which is derived from digital elevation model has got lot of applications in natural sciences, including in civil engineering, earth sciences, environment, etc., even in social sciences. And as you know that it is measured in degrees from north to again go back to the north, starting north with the 0 value, and then of course 360 degree again due north, coming full circle. So, this is how measured, but you can address instead of 0, it is addressed as north facing slopes, and then maybe the south facing slopes, north, east, south, west, and all in all 8 directions this is done. And now as I have already mentioned that flat areas in output image will have a value of -1, and that indicates that it is a flat area, it does not have any sloping surface, and therefore it does not have the aspect. So, this is a, you can call as a no data value, just to indicate to the system that this is a flat area. So, whenever you use, you must check all these things before you go for the next step. Suppose I have used a digital elevation model, I have derived aspect, and now I should check whether I am getting correct results or not. And the value of each cell in an aspect data sets indicates that the direction of the cell's slope faces, because this is after all raster data, and each cell will have its value about the aspect. So, this is how it is handled in GIS. Now, another very important parameter, more detailed discussion we will have on aspect and slope when we will be discussing different derivatives of digital elevation model in this course, in the later part of this course. But for time being and completeness from measurement point of view, we are discussing here also in very brief. So, after aspect calculations or measurements, we go for the slope calculations. One thing that slope can be calculated in 2 ways. Either you can calculate slopes in terms of degree and or in terms of your percentage. That means rescaling, instead of 0 to 90 you rescale to 0 to 100. Both ways most of the GIS softwares will support to display the values in both ways. That means in degrees as well as in percentage. Basically, as you know, theoretically, what is basically slope is that rise over run. That this is the rise, and this is a simple trigonometry. That rise over run is there. That this much rise is here and this is run. So if I want to calculate in percentage, then I have to multiply rise over run, multiply by 100, I get the answer in percentage. If I want to measure in degree, basically it is a tan theta, and that is rise over run, and by which I can get in degrees. Now if I go for degree slopes, like in this example, I am getting this is 30, or in terms of percentage, because it is rescale, so I am getting 58, and likewise different values I can get it, and depending on how you are trying. But same digital elevation model as in aspect case I took. Now if I drive a slope map for that using that digital elevation model, this is how it is going to look. Now it depends on me to how to display my output map. I can have classifications like 0 to 7, 7 to 15 and so on, or I can have just few classes, and this basically this method is called reclassification, that we will discuss little later. So how I want the output, I can control through the classification techniques or reclassification. So basically slope is the maximum rate of change between the each cell and its neighbors, because it is considering what is the neighboring cells are having values. If neighboring cells are having say lower value, whichever will have the lowest value in among all 8 directions of a central cell of a digital elevation model, then whichever is having the minimum, there the slope will be there, or the vector will be drawn. So for example, the steepest down slope descent for the cell, the maximum change in elevation over the distance between the cell and its 8 neighbors. 8 neighbors are considered. That means north, south, east, west, northeast, southeast, southwest and northwest. So all 8 neighbors are always considered in case of slope measurements also. And every cell in the output raster, that is your slope theme, has a basically slope value, and it will carry the slope value. So if you click on any of these cells, and then you will get the value whichever the cell is bearing. Of course, if lower the slope value and the flatter the terrain, or higher the slope value, the steeper the terrain. So these will definitely indicate. It's a very useful, again like aspect, this too has got sloping parameter. Slope parameter is which is again derivative of a digital elevation model, is a again very important parameter for various studies which I had discussed earlier with aspect. The same way there also in the soil erosion, maybe in the landslides, maybe for recreation, maybe for many applications where slope data or slope inputs are required in the analysis. And of course the output slope raster can be calculated as percentage or in degree of slope. These options will always be available in most of the good GIS software. So these were basically primary analytical operations which we perform on a GIS database. Once the database is ready, we may perform some secondary, and what are those secondaries? Which are the advanced compound procedures. Sometimes we may use the macro commands or modeling or expert system techniques. It depends on again our requirements, because what we are having after installation of GIS on a hardware, what we are having is system which is without any data. That has to be the database has to be generated by us for our requirements, and once that is there, then we have to find how to use that data for our project, our purposes. And for that purpose, we may go for very advanced compound procedures, modeling, or maybe employing artificial intelligence or expert system, any other thing. So this is one way of classifying GIS operations, analytical operations. That means in primary or secondary category. In some literature you may find people divide in these two, like the title of this particular discussion was the pre-processing. So, pre-processing, that means preparing your database, spatial database for real analysis. So, it is basically equivalent to your primary operation, and then another one is called processing. It is not post-processing. So, it is processing or real analysis, which involves your advanced or compound analytical operations, which may imply, which you may go for modeling or any expert system and other things. So, what we consider in pre-processing? Some of the, like in primary we have considered pre-processing, because I am covering both way of classifying our analytical operations, because in literature you may find in some book or some on some site you may find little differently and some way or other. So, I thought that I will cover both way of classifying. So, in this kind of pre-processing, the first is format conversion. Format conversion may be from analog to digital, that is also considered under format conversion. Format conversion may be from DXF, which is generated by AutoCAD, or design file which is generated by MicroStation, into the GIS, that it means in the shape file or a shape file in case of ArcGIS or some other software, but most of the GIS softwares honors, respect or incorporate shape files. So, there is no issue. So, from either from DXF to shape file or your design file to shape file, that may be also may come, this kind of operations or pre-processing steps may come under this format conversion. If I am having raster data, there also I may convert, like from format, like I may get the data in TIFF, I may convert into GeoTIFF, means I am having now geographic coordinates, or I may convert from GeoTIFF to IMG, which is a ADAS imaging format for raster data, which is very compatible with like ArcGIS or many other softwares. So, in case of vector data, shape files have become almost universally acceptable shape files for vector data, and same with the raster data, IMG files or TIFF files have become universally acceptable formats for raster data. So, many times we get the data in different formats and we try to convert the data. Only thing which one has to remember, while converting from one format to another, all these formats are not truly transparent conversions. They may introduce some errors, like for example, DXF to shape file. There may be because DXF may not carry your attribute files, whereas shape files carries your attribute. So, you have to be very careful while converting it and must check with the results. So, that statement always true, that after each and every step check for errors, check for accuracy, how accurately the conversion has been done. If it is satisfactory, go to the next step. Now, next is the data reduction and generalization. That data reduction, that does not mean that we will delete the data, but it means that we would like to perform some redundancy checks or do some generalization. We will have more discussion in this lecture little later. And then error detection and editing. After each and every step, check for errors, that is the error detection, and if found, do the editing, correct it and then move for next. Like if I have digitized something, now my topology has not been constructed properly, so I should check for errors, construct the topology properly and then go for the next. Merging means by if I am having two maps and side by side they are like two topo sheets having adjacent numbers, then I want to join them, that is also called merging, but in raster data merging has got different meaning. So, we will be discussing this also in detail. And then edge matching, if you are having two adjacent topo sheets data, then sometimes because of projection issues, the edges, that the data on the boundary may not match very perfectly automatically. So sometimes manual edge matching is also required. Then reclassification, rectification, registration and georeferencing, that we have already discussed this part under this georeferencing category in detail. We had about an hour discussion on this. So this part is already covered. That is also considered under primary operations or pre-processing. Interpolation we have not yet discussed. So interpolation also comes in this pre-processing category. Basically this is, interpolation is that from discrete data you would like to prepare as a continuous data through interpolation techniques. And in major input in interpolation technique is your point data, and rest the techniques which you choose and other parameters. This is another very important pre-processing step, image or photo interpretation. Unfortunately, in recent years, people have started giving less emphasis on image interpretation. Whereas in my opinion, through my experience, I find that it is very, very important that one should analyze the images, satellite data or aerial photographs, and then perform image interpretations as well. Don't leave everything for the machines to do it, because machines do not have intelligence. Only humans are having better intelligence compared to machine. So we should apply our interpretation keys and do the interpretation. That will give us a very good results in our projects. So first I will take the data generalization or data reduction. Here if I take the example this on the left side, the red lines which you are seeing here are not the original data. The black lines are the original data, red line is the smoothened line. And when you would make a smoothened line, that means you are removing certain errors from here, and then you are removing some nodes from here or inter nodes from your polyline, and as you can see here that this black line or polyline has gone near the, or that has become like red line. So if there were nodes, many nodes here, they have all disappeared and only you are having now curved line. So generalization may smoothen your line, polylines. Sometimes it is very much required to perform. Therefore, these tools are supported in GIS. Another example here, like this is point removal means node removal. So the blue line is your original data, and it has, while digitizing, it has created very zigzag appearance. Whereas I don't want that kind of detailed data, I want a very simplified one. So simplified one is the red one which you are seeing. So the same way, if I want a more accurate representation of bands based on that data, the same way it can be done. So band has been preserved of original, but rest here things have been removed. And while things are getting removed, I am removing the nodes and internodes. And while doing this thing, I am reducing the data. That is why data reduction, and same time I am achieving generalization. Another example, this is before line coordinate thinning. Some softwares in some literature they may use word coordinate thinning. Coordinate thinning means again removing internodes from your vector data or polyline. So here you are seeing that lot of nodes are there, but here only the important nodes have been kept, and small nodes which are not that important from generalization point of view are preserved, are kept here, rest have been deleted. Again, one advice here is never delete your original vector file, because vector data is expensive to create or to buy. So vector data is you must, and doesn't require much space also as compared to raster data. So you may perform data reduction or generalization or coordinate thinning over your vector data, but always keep the backup of your original vector data. Do not delete. You may use this right one which is generalized, but you must keep this one in your database all the time. Now, more or less a real example here, that like if you scan a topo sheet, or once it has been digitized, all layers are here, it looks cluttered. I am not interested in that detailed information for my project. So, what I want, just simple road network, rail network, some streams. So, only 3 themes or 4 themes have been kept here. Water bodies are also here. Then water bodies includes the streams, then the rail network, and then roads have been there. Whereas there were lot of other informations which were not required for my project, so those have been removed from my database. But again, this file must be kept, and then this file should be used, because otherwise creating vector data is really very expensive. So, that way what we achieve data reduction as well as generalization. Our maps may not look cluttered, because here lot of information which is not required for my project output. Many times we find a lot of details available along the coastal boundary. Now, I do not want those much details in my map. I want more smoother appearance of my map. So, I may go for generalization. Of course, when you attempt generalization, you are compromising with accuracy, and that is why I am saying do not delete your original data that may be more accurate than your generalized data. So, always have a backup of that one, and then you can perform and use it. So, generalization depend on, again, a scale also matters. So, at this scale, all details about the coastal lines are here, but at this scale those details I do not want, so I will perform the generalization. So, there are many such things are there, like here, depending on again on scale. So, this is initially scale 1:1000. Now, when I go for smaller and smaller scale, that means this the value on the right side of the ratio increases, then it becomes a smaller scale. So, if I go for this, I do not want so many details, and see these buildings which were shown here all have been merged with a single line, because at that scale those details are not required. But if I keep, then it will the map will look very cluttered, and when it is not required, why to keep it? So, generalization or data reduction is performed depending on my output targets, output scale, and based on my project requirements and analysis. So, generalization must be performed. Another very good example of that, this is my input data. Now, I can do the size reduction something like this, that everything has been reduced, especially if you focus on this blue block like this, or I can do the displacement, I can go for elimination, again the size reduction. So, there are various ways people have implemented for generalization, because there cannot be one fixed way. So, mathematicians have always venturing in these areas, and they try to give us new solutions for generalization or other operations. Many such examples are here. This is, if I take this one, then see when it got generalized, all these 3 bodies, water bodies if I say, have been merged into one at this scale, and the same with these houses, they have been merged as a one block. So, depending on the data, depending on my requirements of output scale, I may perform generalization. Now, generalization, if I want to define, then it's a holistic process due to its subjective nature, and because it is subjective, which how it will be merged, as I have shown in previous example like this one, whether generalization I will go for displacement, elimination, or size reduction, in this way. So, that is why I am saying that in this definition, that it is subjective nature, and the lack of well defined rules to guide the decision making necessary to compensate for the visual problem. So, if you are going for generalization of a polyline, then not many problems will be there. But if you go for generalization of polygons, then because of the subjective nature, some problems may arise. So, one has to be careful about that. Otherwise, there is no well defined rules exist in GIS, depending on how GIS developers has implemented these generalization rules. And this is sometimes you may find a very challenging process to understand how to generalize and when to generalize and why to generalize. Why to generalize, as I have said, if change in scale is there, I am going for large scale to smaller scale, I do not want too many details, I will go for generalization. When to generalize is important, as one should not go in the beginning of a project analysis or modeling, but later on one can go for that one. And how to generalize will remain a question, especially with polygon data, but polyline data, that is not a big issue. And these operations differ in terms of accuracy, quickness and complexity. Means how efficient the system and these generalization algorithms which have been implemented, and accuracy. Accuracy part I have already discussed, that must check. Once the generalization is done, must check whether it is giving satisfactory results as per your project requirements or not. If yes, fantastic. If not, then you go and try with some other options if they are available. Now, data generalization, some types of generalization which exist in theory, many of them have also been implemented in GIS, like you aggregate the points, create polygon features around clusters of approximate points. Aggregate polygons, we have seen some examples of means combining polygons within a specified distance of each other into a new polygon. We have seen that example. Now, collapse dual line to the center line. If it is say dual line for rail track or any other thing, you may merge into one line or drive a center line from dual line. And maybe collapse road details, too much details in a particular scale about the road are not required, so you can get rid of them and during your generalization process. There are some other types of generalization like delineate built up areas, create cartographic partitions, merge divided roads and simplify, because there may be a 2-lane road, 4-lane road, you want to merge as a single line in your output map, because your requirements are just to show that there is a road. Your requirement is not to show that it is a 2-way 4-lane road or 2-lane road. So, if it is there, you can generalize and create it just single line, or simplify buildings. Buildings may be represented through polygons, so you can also simplify, merge into a block or a larger polygon. Now, there are other for simplifying line for polylines, simplify polygon, smooth line. We have seen the example of smooth line, a smooth polygon. If there are too many details along the polygon, we can smoothen in. Thin road network, this we have already discussed this part. Now, one important thing when we go for digitization, how digitization will be done, that suppose I have scanned a map, say Survey of India topo sheet. Now, it is in the background of my screen on a GIS platform. Now, I want to extract say polylines which are contours or road network or a stream network from that. So, while doing that digitization part means in the background I am having a raster image which is nothing but the topographic map, and in the foreground I am digitizing say lines or polygons. So, there may be some errors, and as I have been saying, the errors should be they should be taken care about immediately at that moment. What kind of errors you may encounter while digitizing, and people have given names in literature which you will find like dangles. This line supposed to be straight line, but somehow because of some extra click there is a gap and a sort of displacement which has occurred. Our geologists may call as a fault, which was not intended, but somehow it has been created. Same it is the stitchbacks. It's supposed to be a straight line, but it is somehow during digitization process error is got, or maybe a knot, maybe loops, maybe overshoot, like opposite to dangles, overshoots. Again the line should have been like this, but these are now two separate lines and overlapping each other. If I am going for a polygon and digitization, or there I may find a overlap or a sliver, that means the gap between two polygons. So this polygon was not intended, this is an artifact and this is an error also. So this must be removed. Similarly, other errors which I have just discussed should also be removed in order to have a quality in our data, because if these error continues during analysis and modeling, they may give us completely wrong results. Here I was expecting only say 2 polygons, I am now having 3 polygons. So the area, perimeter and centroid for the third polygon, which is artifact, which is due to error, will always be calculated, and everything may go bad. So one has to really take care about this. So with this we come to end of this discussion about pre-processing part 1. Thank you very much.